Thanks, Davey. So this one is, in theory, this is easy. Y prime equals jy is easy. And x equals qy is then easy to do as well. So the key thing is you have to find the q and the j. Does everybody remember? I guess this is the other equation. Q inverse AQ equals j.
I don't know why.
You're going to find it. You're going to find it. You're going to solve for it. Everybody with me on this? Well, let's go through it. Let's see. Yeah.
Would you be likely to give us the eigenvalues given?
I could. I might give you the lambdas just to make sure you get them right. I did that with my 250B class. Of course, you guys.
You shouldn't be doing computation.
I really, yeah. I don't want you like screwing up the whole problem because the lambdas are wrong. Maybe don't do that here.
That's why I got the.
Why don't we practice that philosophy?
Let's practice cheating.
Let's practice cheating. Right. All right, so here you go. The only eigenvalue. Oh, do you know any relationships on the eigenvalues of a matrix just by looking at the matrix?
What? The diagonal?
Do you know facts about eigenvalues? Yeah, what about the diagonal? Okay, if the matrix is upper or lower triangular, which this one is not, then the eigenvalues would be on the main diagonal. That's true. But what else do we know about the eigenvalues? If they're distinct, then the matrix is guaranteed to be not defective. In other words, it is diagonalizable. Even if an eigenvalue repeats, though, the matrix might be diagonalizable. That's not the fact I'm looking for. I'm looking for something that just kind of just check that you did your lambdas right.
Oh.
Go ahead.
Something to do with a determinant?
Yes, something to do with the determinant. How are the eigenvalues related to the determinant?
You multiply them and they equal determinant.
Right, the product of the lambdas is the determinant of the matrix. So we could take the determinant. How would you calculate the determinant of this matrix?
Do it with the bottom row.
Go back or expand the bottom row. We didn't really talk about this semester, but just 1 times this little 2 by 2, which is -1. So the determinant is -1. Okay, so that's actually worth knowing. The determinant of a matrix is the product of the lambdas. Now, does anybody know any other facts?
The trace is the sum.
Right. The trace of the matrix. Everybody familiar with the trace? It's the sum of the main diagonal. Adds up to the sum of the lambdas. So if I add all of the lambdas together, I get the trace. So the only eigenvalue here is -1. I'm just going to give that to you. See, I know that they add up to -3. And their product, so you're thinking, I have to have 3 numbers that add up to -3 and whose product is -1. Because the determinant of this matrix is -1. So does that work? -1, -1, and -1. Those are my lambdas.
Yes.
You good with that?
Sorry, and you said that's true for all?
This is always true.
All matrices.
That's always true. Did I state all this before?
Yeah.
You did, that was the session too.
In another review, okay. Never did it in class maybe. But it's just a little trick. It's worth knowing. Actually, one of the parts you proved. The determinant one I know that you proved. Everybody remember the good old characteristic equation? Right? The roots of the characteristic equation. The roots of the characteristic equation are precisely the eigenvalues. So that means that these eigenvalues, they all factor out. And I'm subtracting t because you're subtracting it from the main diagonal. If you now just put t equals 0 into both sides of that equation, you get the top formula there. Okay. Anyway, I don't want to dwell on that too long. So let's suppose this is given. You know that lambda is -1 3 times, right? So what do you do next? Right, you find the Eigen Vectors, and you try to build the matrix Q, right? So to find the Eigen Vectors, what do I do? The null space, what matrix do we build?
A minus negative 1 off.
And I write null space, but the book, of course, just writes n. Either way.